Okay, section 1.7, it's called the chain rule. Our objectives here are to find the composition of two functions and to differentiate those using the chain rule. Okay, the chain rule is basically just an extension of our other rules. We're going to be using some of those as well. So we've talked about basically your basic power rule, your sum and difference rule, your product rule, and your quotient rule so far. So the chain rule is really going to be used to find derivatives of composite functions, specifically composite functions which can't be simplified or just can be made easier by doing this particular method. So some of our vocabulary, and you've already heard me say it, function composition and the chain rule. So the idea is this: if we wanted to take the derivative of the function that you see here, which is this x squared plus 3x minus 7, all raised to the fourth power, that's kind of the big part right there that's going to make the chain rule worth actually doing. You could multiply x squared plus 3x minus 7 times itself, times itself, times itself, times itself. That's what to the fourth power means. That's going to be a real mess. Or you could break it up in some way so that you do x squared plus 3x minus 7 times x squared plus 3x minus 7 to the third power. You'd have to do the product rule a few times by doing that. Oops. So we could do any of those methods. Those all work here because it can be done that way, but man, are those going to take a long time to do. So there's another method that we can do, and that's called the chain rule. Now, if you take a look at the next thing it says, what if we wanted to differentiate this g of x, which is the square root of 1 plus x cubed? That one, unlike the ones above it, cannot be simplified any further. You can't use the product rule. You're kind of stuck. You have to come up with some other way to do this, unless you go all the way back to the limit definition, and even in that, this is going to be a real mess. So what we have to do is we have to look at the composition of functions. So a composition of functions basically is a function evaluated in another function. So if we were to say f of g of x, which is that notation, which just happens to equal f of g of x, which is also that notation, it's easier for most people to see this one because clearly here you can see that that g of x is plugged into the parentheses for the f. The first notation a lot of people call it the fog notation because it kind of looks like FOG, even though that little circle in the middle is more like a degree symbol. It actually doesn't mean degrees, it's just the of notation. But either way is perfectly acceptable, and you might see it written either way. They both mean f of g of x, where g of x is plugged into the function for f. Okay, so g of x is the the inside function, f of x is the outside function. When you compose those, one is plugged into the other. So the example, f of x is x to the fourth, g of x is x squared plus 3x minus 7. If I want to do f of g of x, I am literally going to take the x's, this x right here, take it out, and in its place, I am going to put x squared plus 3x minus 7. So f of x squared plus 3x minus 7 is x squared plus 3x minus 7 to the fourth power. We are just substituting all of this into that x right there, and you get that one. Okay, another quick example. If I take f of x equals the square root of x, and g of x equals 1 plus x cubed, then f of g of x is taking, all of this, plugging it in to the x right there. So then you're going to get the square root of 1 plus x cubed. So here is the chain rule as far as how you deal with derivatives. The chain rule basically is you take the derivative of the outside function and then you multiply it by the derivative of the inside function. So the chain rule states we are going to take f prime of g of x and then multiply that by g prime of x. So it's the derivative of the outside piece, which is the f piece. You still have to leave the g of x in there because you got to evaluate f at something. And then you multiply that by the derivative of the inside piece. Okay, and then you can go ahead and read this little cartoon here, and just kind of something that we put in there. I thought was kind of cute. All right, let's go ahead and practice these because really they just take practice. And the biggest thing here is understanding where the composites are and what rules you might have to use, because you may have to combine rules, as you're going to see in parts B and C. All right, and the first one's pretty straightforward. Hopefully you can see that there's something inside the parentheses, and then that's raised to the fifth power. So what's inside the parentheses is basically like your g of x. What's outside the parentheses is basically like your f of x. And some people like to write all that stuff out. To me, it's a little tedious, but if that helps you, by all means do so. For me, it's easiest just to see, okay, what if I were to just cover all that up? I've got something raised to the fifth power. So if I want to take the derivative of something raised to the fifth power, it's 5 times that something to the fourth power using the power rule. Well, now we kind of got to see what I just scribbled out there, because that still gets plugged in here. That's the something. But then you have to multiply that. Okay, now we're actually done with this, so that's no longer a part of it. We just finished that part. Now we have to multiply it by the derivative of what's still left in the parentheses. And that's the derivative of 1 plus x cubed, which is 3x squared. And we're finished. Whoops. Okay, come on. What's going on here? Just trying to erase. There we go. All right, there we go. That's our derivative. We don't need to simplify it at this point. All right, part B. Part B, you have to recognize a couple of things. First of all, I have multiple functions there. I've got 3x minus 5 to the fourth, and I've got 7 minus x to the 10th. Both of those are composite functions. I've got two parentheses where each one of the parentheses is raised to a much higher level power. But those two things are also being multiplied together. So really, we're going to have to do a product rule as well as a chain rule. This is really where you have to be careful. So in this case, if I read this left to right, I do have a composite function multiplied by a composite function. So the product rule takes precedence, but within the product rule, we're going to have to do a chain rule. So let's see how this works. This is our first function. This is our second function. When I take the derivative of the first from the product rule, I have to bring the 4 out to the front, reduce the power by 1. Okay, that's just the outside. Now I have to multiply that by the derivative of the inside of the 3x minus 5, which is just 3. That's just the derivative of the first. Product rule says we multiply that by the second function. Plus, we do the derivative of the second function. Okay, so now I'm going to bring the 10 out to the front. Keep the inside the same, reduce the power by 1, times the derivative of the inside of that, because I'm still dealing with the chain rule of that part. Well, the derivative of 7 minus x is just going to be negative 1, because the 7's derivative is 0, negative x's derivative is negative 1, times the first function, which is 3x minus 5 to the fourth. So I'm going to underline a couple of this. This was the derivative of the first times the second, plus the derivative of the second, using the chain rule again, times the first. Okay, let's do one more. So this one here is the fourth root of x plus 3 over x minus 2. In this case, that fourth root is kind of the outside piece. The x plus 3 over x minus 2 is the composited piece. So here we actually start with the chain rule. Oops. Well, why it keeps jumping around like this? I'm not touching anything that I know of, but maybe I am. So f prime of x. Remember, a fourth root is the same thing as the 1/4 power, so I'm going to bring the 1/4 power out to the front. I've got the entire inside of this thing now raised to the negative 3/4 power when I subtract 1 from the exponent. But I'm not done because I have to do the chain rule now, which says to multiply that by the derivative of the inside. But x plus 3 over x minus 2 is now a quotient rule. So now I have to do the quotient rule here. So the derivative of the top is 1 times the bottom, which is x minus 2, minus the derivative of the bottom, which is also 1, times the top, which is x plus 3, all over the bottom squared. And that is your derivative. Okay, no need to simplify in this case. You can definitely simplify the numerator of the second parentheses if you want to, but I'm okay with it at this point for that one. Okay, and again, your textbook calls this some kind of weird extension power rule or whatever. No reason, like it says there, to change names. It's just a chain rule in a slightly different form, I guess, but we just call it the chain rule. Example number 2. A new smartwatch is placed on the market. Its quantity sold N. Its quantity sold N is given as a function of time t in weeks, where N of t equals the function that you see there for t is greater than 0. Find N prime of t, then find N prime of 52 and N prime of 208, and interpret these results. So first of all, let's find N prime of t, because we can't find N prime of the two numbers until we get the general derivative here. So it is definitely a quotient, so we're going to use the quotient rule. And when I get to the denominator is where I clearly have a chain rule, because I have a composite function there, something raised to the second power. So let's go ahead and do the quotient rule here. So the derivative of the top is going to be 500,000 t times the bottom, which is 2t plus 1 squared, minus. Now the derivative of the bottom is a chain rule. Bring the 2 out to the front. Reduce the power by 1. I'm not going to write 1 as my exponent because it looks like a prime symbol. Times the derivative of the inside of that, which is 2. And then times the top function, because I got to finish off the quotient rule. All divided by the denominator squared. Well, if I square something that's already squared, it's now to the 4th power. Okay, again, I don't really need to simplify that. I do, however, need to plug in 52 and 208. So let's see what we're going to get there. We're going to do N prime of 52 and N prime of 208. All right, we're going to plug those into a calculator and see what we're going to get. All right, so let's see. At 52, we're going to get, it looks like 22 point, rounding 46. And then at 208, if we plug that in the calculator, it looks like we're going to get approximately 1.43. And what do these things mean? Well, T stands for time in weeks. So that means at 52 weeks, and N prime means, well, N itself is the number sold. So this is how the number sold is changing. It's the derivative. It's the rate of change. So the number of, what are we selling here? Smartwatches. This number of smartwatches sold at 52 weeks is changing by approximately 22.46 smartwatches per week. And then at 208 weeks, so 52 weeks, by the way, is a year. No, 52 weeks in a year. Had to think about that one for a second. And then 208, I guess, is 4 years. That's 4 years. So basically at 4 years, the number of smartwatches sold is changing at 1.43 per week. So it's going up much faster after the first year, and then after the 4th year, it's going up much slower rate. So that's what it means. All right, I guess that was it for 1.7. I was getting ready to go on to 1.8. We'll do that in another video.